happy to be here. I've been away from CAM for less time than I was at CAM, so that's still a fun thing that I can say. I'm going to talk about 3 different researchy projects that I've been working on in the last couple of years, hopefully at a broad level to give you some idea of some of the things we're thinking about and some of the challenges in essentially making complex systems and complexity science useful to the government and decision makers and the folks who actually can do something about the world. So at the beginning, I'm going to tell you a little bit about MITRE. I knew nothing about this until they called me in December and asked me if I wanted to interview after I forgot that I had applied to them. MITRE's been around for over 50 years. We are a not-for-profit doing science and technology research and systems engineering for the federal government. We are a trusted advisor, and by that I mean we operate what are called federally funded research and development centers. We operate 7 of them that are here. These are long-term 5 to 10-year contracts with a particular agency that put us in the role of trusted advisor, meaning we can evaluate other contractors' work because we're not competing with them over building a new sensor or building a new ship or any of these sorts of stuff. So we're the government's partner in this sort of regard. It's hard to see. I've worked for about 4 of these. So I've worked in the national security domain quite a bit. The Center for Enterprise Modernization, that is primarily VA, IRS, and Census, all of which have tremendously hard technical problems that they're trying to figure out how to do. I'm not going to talk about IRS today, but I'll say this. I actually think IRS is one of the most successful agencies in the government, which isn't very popular right now to say, but they successfully process 300 billion tax returns every year in a 2-month time frame and send out all of the money on time every year consistently for decades. And that's sort of an amazing accomplishment when this is 90 different computer systems, some of which are written in Cobalt, all strung together in order to process tax returns. I've also done a little work in the judiciary around public policy, and I'll talk about that today. And then quite a bit about homeland security and in particular critical infrastructure protection. So we work with a whole bunch of different people in sort of a trusted advisor, doing objective and independent research in the public interest. What I want to talk about today, so there's a smaller group of us who want to do complex systems, and as I said, sort of make complex systems and complexity science useful. So the idea here is that the academic work in this is relatively immature. There's pockets of this being done at the Santa Fe Institute and other various places, but it's not a really well-established domain. So a lot of what we're trying to look to do is sort of bridge the gap between what academics are doing and what is needed by the government in order to make better decisions. Because right now, a lot of decisions are made based on expert opinions and not modeling and analysis, which is a real shame. So this is using things like agent-based modeling, dynamical systems, things to find tipping points and bifurcations, using complex networks, and I'll show a graph of all these stuff in a little bit. And the other side of it is sort of evaluating and implementing and improving academic work. And I'll talk quite a bit about that as well. So trying to figure out if algorithms in academic work are ready to actually be used in a control system or a decision support system, and trying to do the research to get it there. We have our own internal research program that's a competitive program where we do a small amount of internal research. Quite a bit of what I'm going to talk about is that. And we have some academic collaborators in this sort of an area. We actually have someone on site at the Santa Fe Complex Systems Institute out there, working with them, trying to figure out what we can do jointly with them. We've got somebody else at the University of Vermont in their Complex Systems Center, some work with MIT, and some work with George Mason on agent-based modeling. The 3 things I'm going to talk about today are trying to find tipping points and bifurcations in complex systems, and sort of a cautionary tale about that. Using network science and simulation models to look at resiliency and risk in critical infrastructure. And the third thing is, can we make network science useful in public policy? Which is a very interesting thing, and I'm running a research project in that area as well. So, set the stage at the beginning. What are complex systems? There's a wonderful book by Melanie Mitchell about complexity that basically says at the beginning that nobody agrees on a definition of complex systems. A computer scientist will say it's all about information theory. A physicist will talk about entropy when you're talking about complexity. So I like to think of it as a way of thinking about a set of problems that are inherently nonlinear. They're usually networks of things interacting. There is cascading failure from one to another, and there's emergent behavior. So ants are a wonderful example. You take a small set of ants, set them on a table, they'll walk around until they die. Get enough ants, they'll build a bridge between the two tables. So there's a phase transition in ant behavior where enough of them are more than the individual ones. And we can see those sorts of things happening in a variety of different areas. Another way to look at complex systems, it's a set of disciplines trying to work together and come up with ways to think about problems. So I come from the nonlinear dynamics background. A lot of my interest now is in making networks useful. That's why those two are highlighted. We do quite a bit of work in the social modeling, building agent-based modeling of citizens and society and that sort of stuff. So it's sort of an inherently interdisciplinary thing, which is why it's really interesting coming from CAM, because CAM was another interdisciplinary place. So I've gone from interdisciplinary to interdisciplinary, which is sort of fun. But we've got these multidisciplinary systems, but they're very difficult to predict and to predict their behavior. So if they're anyway chaotic, you've got sensitive dependence on initial conditions. You've got to figure out what level of model is going to approximate reality enough to get some sort of a decision out of it. Of course, if there's people involved, you've then got to figure out how do you model human behavior, which is an unsolved problem in this whole area in and of itself. So there's a lot of interest in predicting when large-scale changes are going to happen in these sorts of complex systems. And we've been doing some work in trying to figure out if we can use any of the ideas from bifurcation theory to look at what's going on near critical transitions to see if they're predictable. So when you approach a critical point, there are some generic things that happen in these sorts of bifurcation in bifurcations. And there's a couple of different approaches you can take to look at these sorts of things. So there's an idea about critical slowing down, which I'll talk about on the next slide, looking at the behavior systems near tipping points. And then there's scale invariance. When you go through tipping points, a lot of power law behavior emerges. There's some really interesting things with multifractals when you're looking at competing processes as you go through bifurcations. And then there's also this idea of universality. When you're near these sorts of things, you get generic behavior regardless of the type of system you have. So we did a research project for about 1.5 years looking at critical slowing down. So there were a number of these studies in Nature, primarily looking at climate science, where they said, okay, in complex systems, they're all when a system of these is going through a bifurcation, that is preceded by a time period when the system is critically slowing down. And the idea of this is that in this really toy example here, as this energy well here becomes flattened out, small perturbations will take longer and longer to recover. So before the system goes through the bifurcation, if you could perturb it a little bit enough and measure how long it took to recover, then you could try to measure how close you are to that bifurcation. And of course, in real systems, you can't perturb it a little bit over and over to figure this out. So there's a bunch of papers about using metrics like the coefficient of variation and skewness and autocorrelation, and increases of those being correlated in some way with bifurcations happening. And this is a simple toy example of one of these. This is a synthetic, this is a stochastic ODE that I wrote that I forced through a bifurcation, and these are the measures of these metrics, and you can see as you get near here, the skewness increases and the autocorrelation increases. And that in these papers, they aggregate these things into a moving average and use this W2 statistic and a 2 standard deviation window to say, these are the areas where we're near a bifurcation. So there's issues with that, fundamentally. The first sort of issue is these are not areas, we're not measuring if we're near a bifurcation, we're measuring if these statistical metrics are high. So they could be high for other reasons. But we had a little bit of success applying this sort of stuff to some social data and some other sorts of stuff. So we extended that sort of algorithm to, so basically you have to take a moving window and slide it over your data and measure some statistics on that. So we extended it to look at a multiple set of moving windows. And this is a little bit of results in doing this. This is, unfortunately, I have to explain it in this way. This is some sentiment information about blog posts in a country where they don't speak English, where there were protests going on that were very serious a number of years ago. And because of some stupid internal politics stuff, I can't tell you the country, when this was, or what language they were speaking. But it was 6 years ago. So,
what letter did the country start? No.
Well, it's in the news a lot right now.
Interpreting code by now.
All right.
Yes. So this is essentially the number of blog posts that were happening in this particular language, and this is the negative sentiment score of this, and this was the date of this really large protest. And we found that by varying the window in this, we could get some interesting correlation into the lead up to this type of protest. And this is so the protest happened on this day, but there was a lot of unrest before that, so this wasn't an incredibly surprising result. What gave us pause, of course, is this wonderful point over here where, so this is half of our moving windows are detecting something weird going on here. The big issue with these sorts of algorithms and using this to make any sorts of decision is if I run this over the entire course of the year, I get a non-trivial positive rate. So what does that mean? That means that the system is behaving statistically different at these different periods of time away from a known large-scale event. And that's part of the problem. The other problem is, of course, if you're measuring a real system and you're trying to measure being near a tipping point, there is no such thing as a false positive. Because you're measuring, so your system could approach the tipping point and walk away from it. If you detect that, then that's a good thing. But if you don't have a model of your system, there's no way to know if that's what you're going on. So in my view, this is sort of an interesting area. The academic work here isn't where it needs to be to make it useful. Most of the papers are wonderful little papers where they have a known event, they have a fixed time period before that, they run their algorithm on it, and they say, I could have predicted this. Run it on a year, and it doesn't work. So we did some other work with this. This is a similar thing, looking at the Super Bowl blackout in 2013.
Could I ask one thing?
Yes.
So if I heard you right, the issue you feel is that there's predictions that are false positives. Do they miss events, these kind of algorithms?
So there's a couple
that did take place?
There's a couple of issues, right? So one is a protest a bifurcation event?
Uh-huh.
That's a separate issue, right? So that's one issue. Another issue is, so do they miss events? Sometimes. They're not perfect in that we don't have a lot of data where there's lots of data when things aren't going on.
Right.
And smaller amounts of data where there is stuff going on.
Oh yeah, but that is seen too.
Yeah, it is seen as well. And you can play with, and of course you can play with parameters in any of these things and make them tell you whatever you want, which is another whole issue. We've got, there's another project somebody else is running. We're measuring frequency of the electric grid at a whole bunch of different MITRE sites at 50,000 hertz, and then reconstructing frequency waveforms of that. So we have like 5 years worth of data at 50,000 hertz for the, measuring the power grid. Power grid is an interesting thing in that the Eastern Interconnect is phase synced, which means within a margin of error, you can measure the frequency of half the country at any outlet. So you can actually measure a global property of the system anywhere, which I think is a fascinating thing. But so this is the frequency during the hour in which the power went out in the Super Bowl in 2013. We ran this thing, and we actually found the most interesting thing was that the behavior of it seemed to change when halftime ended and everyone went back to their TVs. We actually saw a little bit of a spike in our sort of algorithm here around the power went out, but that actually happened in both the Eastern and Western Interconnect, which are largely decoupled. The other issue is when they went back and figured out this was a very local thing that happened there. I'm going to keep going. We worked some on trying to come up with new ways to do this. Most of these algorithms are written in data-poor environments. So if you're doing climate change, you're looking at one sample a year over decades. We have some really data-rich environments like the power grid thing. So we came up with a different approach where we take We want to take our signal and compare it to a control signal and compare the statistics of those two things to see if they're sort of different. And we've had a little bit of success with this. And so here's a little bit of results for that. The top plot is, again, the Super Bowl plot, and we get some similar results there. This is some data that we got from the FNet consortium around the Southwest blackout in 2011. And ignore that this is labeled wrong for some reason. Actually, that's the wrong. Yeah, it's labeled wrong. So right here, the power went out across multiple states in 2011. NERC identified 7 events that led up to it. This was the first one when we got a large drop in frequency, and we did see when we were running this that these parts in here, windows in here, are statistically different. And that's sort of where we are with trying to do these sorts of things. I look at it as kind of what it is. We're looking for periods of our time series that are statistically different than typical behavior. And that can be useful information because the government has analysts staring at large amounts of data, and if we can help them look at specific pieces of it rather than the whole of it, then that is sort of a useful thing.
Are you going to tell us what CSD stands for?
CSD stands for critical slowing down.
Are you going to tell us how your algorithms work?
Sure. So, jump back over to here. So the way in which this works is what we're doing is we're taking a moving window across one of these time series and computing these 3 statistical metrics over these moving windows. And we started out with doing what one of the academic papers was doing, is computing essentially a moving average of these and comparing the current window with the moving average of past windows. And then that ends up with this thing called a W2, where then you're looking for it being 2 standard deviations away from the normal typical past behavior. What we sort of switched to doing was, well, instead of looking at just the time series in time, let's take advantage of the fact that we have all of this data. We can look at a control signal and calculate the statistics of that over a long period of time. And then that gives us a better understanding of when this thing is going to be behaving far away from the typical behavior of those sorts of signals.
And the control signal comes from?
So in a lot of these, for the Super Bowl one, we compared it against the same time the week before and the week before that and the week before that. So you can do those sorts of things. For the FNet one, we compared it against the 14 hours that came before it. So we're really trying to wrap some statistical measures around this. So that's a little bit about this sort of idea of using to look at these sorts of critical transitions. Another thing we're working on is sort of trying to make complex networks more useful, in particular in critical infrastructure. We've got a big project now with DHS looking at the coupling between the financial sector, the electric grid, the water infrastructure, and all of these sorts of things, asking is it susceptible to cascading events between these various sorts of things, and how can we go in and figure out this sort of stuff. So sort of starting at the beginning, infrastructure is probably no surprise. It's got hubs, and it's sort of a small world type of network. And you can build these sorts of networks in any sorts of ways. One example of this is if you just have a whole bunch of wood chips and you walk around. And you find a chip, you pick it up. If you run into another one, you drop it, and that'll end up building a nice hub and spoke type of nice hub network with a bunch of resources constrained together. This sort of stuff exists in Power Grid. They are largely power law distributed in their node degree and all of these sorts of stuff, which means then there's all sorts of interesting questions there. I'll keep going. So, and of course, power grids are interesting because cascading failure is a real problem. We get that the Southwest blackout that I talked about, the root cause of it was someone skipping a line in a checklist of things they had to do, which caused a line to overload 2 hours later, which then caused a substation to overload and then caused the cascading blackout. And we can build very simple models of sort of cascading failure. The typical one is sort of the Sandpile model, where you've got a rectangular grid and you drop sand on it randomly, and if a certain amount of it lands in any particular node of the grid, it will fall to the ones that are connected to it. So here's a nice little example of that. So this is running in NetLogo. In this, we're randomly dropping sand on this rectangular array, and then it's cascading out. And interesting how things happen here, because you actually get, over time, you get cascades across all scales in this. So you get that the size of the cascading failure is here. This is a log plot of that, so you get a nice, what looks like a power law of the distribution. So you can see you're starting to get large scale failures of these sorts of things. So you can build really simple models of this. There's actually a nice board game called Pandemic that's actually a Sandpile model on a network. In that you get cases that build up at various places. If there's 3 cases at a particular place, then they spread in exactly like a Sandpile model out. It's a really nice, simple example of that. So that sort of leads to believe, okay, well then, if we have cascading failure, then that's and we have, these nearest neighbor interactions, then that's a fairly well-studied problem in sort of disease propagation and all of this. If you have something going on here, it will propagate to its nearest neighbor, and so on and so on. So that's sort of a well-studied way of doing it. The issue is power grids don't work this way. So the way power grids work is, so if a line goes out in the power grid, the entire thing rebalances in the next, in real time, because it's all distributed due to Kirchhoff's laws. And people really in the government actually don't really understand this, and that's sort of one of the challenges that we have, is trying to communicate with people that don't have a technical background. So there was actually a Chinese paper in 2009 that looked at and basically said you could attack the very edges of the power grid and cause large-scale cascading failure. And that went all the way up to Congress, and they had a hearing about this. And it turns out the model they had was a disease propagation model, where it just propagated to their nearest neighbors. That sort of a model doesn't really work in these sorts of power grids. You need to take the physics into account. So here's an example of, this is a DC power flow model where it starts out by removing 2 branches in this, and hopefully this will play. So this is a cascading failure. This is actually the Polish power grid. So you can see the red lines are going out, and you can see how they're not connected to each other as they go out. And as this thing goes forward in time, it'll island out into various pieces, or it'll just disappear. That's even better. So the entire left part of this is now disconnected from the right part of it. So this is some work we did with Paul Hines at the University of Vermont, looking at this, and then also trying to overlay a communication network on top of this sort of thing. So we are doing, as I sort of talked, we've got quite a bit of work trying to do these sorts of complex network stuff for DHS. We've got some direct funded work, and we've had a series of internally funded research efforts that have sort of led to that. Some of this has been joint with Paul Hines at the University of Vermont and a couple of his grad students. The idea of where we're trying to get to is to help them do risk and resiliency modeling and analysis of critical infrastructure. So we want to be able to look at the likelihood of blackouts and other sorts of undesirable behavior, help them understand the cost of this and what sort of decisions that they can make. So given the levers and the capital they have to invest, how can they best spend their capital in order to increase the resiliency of this? So this is sort of our picture of what we want to do. Given some of these critical infrastructure things, we want to have a model of it, be able to run designs of experiments on that, and then do risk and resiliency on top of that, and then eventually present it to them in an interface in which they can understand and interact with these sorts of things. But all of this starts back with power grid models. So there's a lot of these, of course. So in some sense, these sorts of Sandpile models are the very simplest of these. And hopefully I convinced you fairly quickly that they're not very useful, because you need to take the physics into account. There's a variety of these here in the middle. There is some work way over here on the right done by some of the national labs, where they have very detailed simulations that take them 6 months to run their experiments that end up with a report that's this tall, that then when DHS reads it, realizes it doesn't answer the questions that they asked. So we think the sweet spot is right here in the middle, where we're taking the physics into account, but not trying to model everything. So one example of this is the OPA model, which has been done primarily by Ian Dobson at Iowa. OPA is Oak Ridge PCERC, University of Alaska. So in these sorts of models, for each time you update the loads that the generated in the line, you have a random line outage, you solve DC power flow for that particular one. If there are overloaded lines, then you test for more outages, and then you go back through the outer loop. So you've got a physics-based model in the middle, and you're running it forward in time. There's a couple of different ones that are sort of similar on this. Excuse me. So what we want to be able to do is, not just for power grids, but for any of these sorts of infrastructures, try to wrap this into something that then can make it useful. So we've got a model here in the middle. We start with a network of something. We can run a model of it, do visualization analysis, end up with some risk resiliency assessment, and be able to go back through some of these loops and be able to do this again and again. So we started doing some of this. This is all work in progress. A little bit about how we're decomposing this problem. So we basically have 4 main pieces to the middle of this. First part is dealing with the data. So ingesting networks for networks that it exists, generating synthetic data when it doesn't, then being able to do analysis on top of that. That's the second one. Third one is to be able to do large-scale designs of experiments, both full factorial or genetic algorithms or any of these sorts of things, to explore the space of what can happen. And then the last stage, we've got a couple of my colleagues who do meta-modeling. So this is so once we have a good understanding of the system, can we have a simpler model that runs faster that can give us similar results? I'll show you a little bit more about this. I should slow down, I guess. So this didn't come out very figure. So this is another picture of this Polish power grid laid out a little bit differently. In terms of power grids, one of the things people are interested in are what are called n-k contingencies. So the electric grid is n-1 compliant, meaning if you remove any node or edge from it, it'll all continue to work. Turns out that the Polish grid is not n-2 compliant. So, and if you run all possible combinations of removing 2 lines, it turns out there's about 10 of them that there's about 10 of them that are in almost all of the large-scale blackouts that occur because of it. And that's 10 out of about 3,000. And there's some issues computationally in doing this sort of thing. If we wanted to look at n-3 contingencies, Polish electric grid is about 3,600 nodes, or 3,600 edges. So then you've got 3,600 choose 3. You want to do 4, it's 3,600 choose 4. And by the way, the U.S. electric grid is almost 2 orders of magnitude larger. So you've got a computationally large space that you're essentially searching for needles in, which is a hard thing. And there's some algorithms that you can use to try to find which pairs of things are going to cause problems. But that's one of the open questions. How do you efficiently search these sorts of graph spaces? Where did my picture go? All right, we'll just skip this. So we've got a paper being presented at Winter Sim in 2015. A couple of my colleagues and I, we built a neural network and a stochastic Kriging. They built a neural network and stochastic Kriging meta model on top of the results of this, and have some promising results that we can use this sort of meta modeling approach rather than having to run all of the simulations every time we want to get information out. All of my diagrams are missing now. Okay, so pretending that there was a picture there, what we want to work towards, because we haven't done much of this, is trying to understand the resiliency of these. So risk, the idea of risk is how bad of events are going to occur. Resiliency is sort of given, is how bad of events are going to occur plus how long it takes to recover. So then we need models that not just simulate power going out, but then we also want to try to simulate even sending trucks out to fix lines and all of that sort of stuff, so we can get a better understanding of that sort of stuff. And I'll show you one fun thing. So here's an interface all built in JavaScript and D3 to try to look at some of these simulations. So we can step this thing forward in time. It refreshes slowly because I'm running it locally and not on a server, but it should refresh. So this is the electric grid for run 8. Let me refresh this. Hopefully my server is still running. Actually, so I'm going to use the other one. I'll just show you this one. This one's all right. All right. Trying to run stuff people are currently working on is not a great time for a talk. So we're working on sort of web-based, JavaScript-based visualizations to interact with these sorts of things. If they were working, go back here. You can interact with the graph, select, look at local neighbors or it's around it, and all sorts of various things. So this is sort of one level of this. This is sort of for an analyst to try to understand what's going on. The other part that we need to work towards is sort of the high-level decision-maker view, because as I've learned working for the government, they have no time to look at anything, and the level of information they have time to understand are essentially stoplight charts. So red, green, and blue. Yes?
Can I ask you a question while it's working?
Yes.
So I took away as an informal thesis in your talk that you were lamenting that there are sort of experts who make sort of overarching decisions based on gut feelings and judgment.
Yes.
And that it would be better if there were simulations. But, looking at sort of things that you introduced, I wonder, are you not just switching out experts for other experts? There are all these tuning parameters, all these different characterizations of networks that don't work, and so you need to know the right characterization of the network and so forth. So are you just sort of pushing the problem down to a different level?
Well, I would argue is if we're doing it based on a simulation model that, of course, is an approximation to reality, we can trade. We may be pushing it down a level, but it's a model where at least we're doing analysis on it. So other examples are, so we do quite a bit of work on portfolio optimization. So there are parts of the government where they just get in a room and decide how much of various things they're going to do and hope that that meets the capability needs that they have.
So at the end of the day, is it any less wrong?
How do you define wrong? I would argue that it's far more defensible. So the idea is that anybody can challenge it. If you have a model of a system and you're doing it in a consistent way and presenting it to people, anybody can challenge it. And if they want to disagree with the model, if you're doing good science and good math on the model, then you can defend it in front of these sort of organizations.
So one thing that jumps into my head was you had this W2 parameter.
Yes.
This was based on statistical measures, and you're talking about some baseline signal. And part of immediately that jumped in the question I asked myself was, what's the signal-to-noise ratio in your data? You know it. And so this is going to be very, very important as you select, how much of each of these stochastic parameters or those statistics to weight.
So if I go back to my original comment and that first example, I would say even the work we're doing is not the type of work we need to be doing. And it's sort of a cautionary tale that they keep saying, well, there's these wonderful papers that say we can predict all of these sorts of things. Well, it turns out you can't. And we even ignored the issue that even if you take the hypothesis that a bifurcation, there is these sorts of things there, it may be on a time scale that it doesn't matter. So if you're sampling every day, but the time scale where this critical slowing down thing is a millisecond, you're never going to see it. So there's all sorts of time scale issues in these sorts of things as well. So this is not going to load. So maybe I'm not online anymore. So we can pretend there's really cool pictures in this, and all of these Java errors are probably why it's not loading. So I think the idea of this sort of thing here is we want to try to put together this system with models in the middle, and then so that they can make model and analytic-based decision making. Using physics-based models in this particular instance, but for other sorts of ones, if they're human systems, then we can build other models and those sorts of things. And we want to be able to do this in a consistent, defensible way. rather than relying on expert behavior with their own biases and those sorts of things, and just putting people in a room and letting them decide what to do. Yes?
So sorry, I have to ask again now, because you said there were these reports from national labs.
Yes.
And these were from high-fidelity physics-based models that took months to undertake. And at the end of it all, they were also not useful. These are even more deeply scientific in their foundations than what you're proposing.
So,
and yet they're equally valueless.
well, the issue is the more detailed you build a model of something, that you have to make sure you're building the right model to answer the questions you're trying to ask. And the government has had issues with some of the, okay, so I'm being recorded, so it's not an issue that they're not doing good science, it's that the results that are being gotten out of it aren't coming at a time frame in which they're trying to make the decisions, is I think one of the big issues.
I have two questions. First one, follow up on that, is how much work do you do to compare your models with real data? With actual data? Do you have actual data that you use?
As much as, so the answer to that question is as much as we can. For the actual grid, we have some. There's actually very little data available in this critical infrastructure domain, partially because it's protected, and partially.
But you're a FF.
Yes, so we're working. So one of the wonderful things about the government is it takes forever. So we are to do anything. So in order for us to get data from NERC about the topology of the electric grid, we had to submit a request that has to go through public comment, and that's taken 9 months.
So the second question I have is, did this project start with under your initiative, or did someone come to you as somebody who's working for MITRE and say, we would like MITRE to study this problem?
This particular thing, so it grew out mostly the lab. So we had a couple. So I ran a research project looking at some of the data around critical infrastructure for about a year. There were a couple of related ones. Those things sort of coalesced into an idea around this sort of stuff. We discussed it with our portfolio managers who worked for DHS in this area, and then from there it sort of grew into this sort of an idea in this area. So MITRE is a matrix organization. So we have customer-facing departments that are focused on a particular customer, and then we have technology-focused tech centers that are focused on technical capabilities. So I'm in a modeling and simulation tech center, and actually in an operations research department of all things, even though I didn't study that. But so we're sort of the technical backbone, and so we sort of work for the program divisions. So they have hard problems, they come to our some of our leadership, we discuss how we can solve them, take them to DHS or someone else, and then try to work through how to do these things. Does that answer your two questions?
Yes.
Okay. So in the interest of trying to cram way too much into an hour talk, I'm going to completely change topics and talk about, this is a research project that I've been running for a little over a year, trying to work on network science and policy and public policy, and trying to make this sort of thing useful. This grew out of conversations I had with some of our the lawyers at my company and other sorts of stuff. And you can see in the news there's lots of things about various parts of the law and various things being too complex. So the tax code is complex, the healthcare law is complex, the Veterans Agency is complex, the tax code is edited hundreds of times every year, including a week before they have to start processing things. They have new rules and regulations they have to build into their software systems, essentially in real time as they're going to be processing things. So, where am I? Okay. I'm going to close this note again. So we came up with the idea is, well, we can try to start understanding these things as sort of a network. Starting with citation networks and building out from there to look at how related various parts of policies are to each other. And one of the sort of interesting and frightening things I've learned from talking with various agencies is they have absolutely no tools to help them interact with policy. So I talked with an agency that shall not be named about what they do, what their group did when they had a new law that influenced their business. The response was they get 5 lawyers in a room with a 3-ring binder with the entire United States Code in it, that they each individually put Post-it notes on the pages they thought were relevant. And that is the state-of-the-art tools that the government is using in this sort of area. So we're sort of, this is an ongoing thing. We're trying to, again, build these sorts of networks. This is an example. This is a hairball network. This is the internal VA policies, public laws, and the Code of Federal Regulations that has to do with the VA processing claims. So that's sort of where we started with this project. These are inherently multi-level networks. So at the top we have things like the United States Code, and then actually below that is the Code of Federal Regulations. Before that are the public laws that are actually passed by Congress. There are interdependencies within these levels and across them. Then there's the what agencies are actually doing, both what they publish that they're doing and privately what they held in private. There should be relationships between what the law says they should be doing and what they're doing internally. Then there are, a layer down is then how they actually then interact with citizens. So in the case of VA, there are a whole bunch of forms that they ask veterans to fill out when they do this. At the very bottom, there are then the citizens who have to then fill out those forms.
Now, what is a VA?
Veterans Affairs. So one of the interesting things is, because we are an FFRDC and we work for the VA, we can get access to all of the claims data for every single claim for veterans over courses of years, which means we can look at which forms have better and worse outcomes down at this level. So we can sort of measure, in some sense, the relationship between forms and wait time and those sorts of things. Well, forms map up to the internal policies. So a conjecture is we can perhaps measure which parts of these network are behaving well and which parts are behaving poorly based on outcomes on the ground. And we're trying to get to this level across a couple of different agencies. So our sort of hypothesis is we can use network models to provide our sponsors and their customers a more objective and transparent view of the interdependencies between the rules that govern their operations. Last year, we sort of looked at a couple of different things in this VA rule space. How does the complexity of this change for different topics? Which claim forms come into comment are often asked for in the same governing laws. So we can, in one way, we can measure how related 2 different parts of this network are by if they're asking for the same form. And we sort of put together some very basic tools to sort of interact and work with this network. First way we did this, since I had a month to prove to my company that we could do any of this, was I did it all in Mathematica, because it's my favorite tool. This is our wonderful hairball diagram again. M21 are the internal VA policies. USC is the United States Code. Code of Federal CFR is the Code of Federal Regulations. Black is the VA forms, and other is mostly public laws. So we have a big network. We need ways to go down and interact with it. So we can pick any sort of a node in this and just explore locally the graph near this node. So, and we can go any number of distance steps away from it. 6 is going to be the whole thing. So within 6 steps of that node is basically the entire network. So we can try to look at the local structure of this around various nodes. But we can also, because each one of these is essentially a document and they're referencing between each other, we can also query those documents and start pulling up graphs that have to do with particular topics. So this is a graph of all of the red squares are parts of the internal VA policy that have something to do with orange. In this context, this is about Agent Orange in those sorts of cases. And these are all of the things that are referenced by those particular documents. So you can see this, some of these have a lot of references. This particular one here is referenced by two of these other ones. And this was sort of our prototype we did into this area. But of course, Mathematica is a wonderful program, but only works on the computer with Mathematica. So what we have now is a web interface connected to a graph database that we can query the United States code and pull up graphs that have to do with these sorts of topics and interact with them. Click on particular nodes. So this is 26 USC 1, which has to do with the tax imposed on married individuals. So this particular graph has, we go and look, we have 191,000 edges and 295,000 nodes. One of the interesting things about our public laws is about half of them don't have references in them to anything else. So this is sort of the stage we're at with this particular part of this. What we want to be able to do is extract the reasons why these things are citing each other. So we have a sort of experimental thing, this is a very basic way we did this. So some of these are because they're giving an authorization to do something, or there's a requirement in one for another, or there's actually a lot of definitions that are pulled from definition sections. There's a couple of guys working on this, trying to use human language technology to extract out the reasons why these are referencing, using word2vec and some of the other popular HLT algorithms that I'm not an expert in. We also want to pull up topics and start trying to relate these things together because they're talking about each other. We sort of got a couple of different thrusts. So, yes?
At any stage, the lawyers that you mentioned with the 3B printing binders and the post-its, at any stage do you bring them in to help you draw that network? Or double check what you found? Or?
We've done some of that. So we're still working on that sort of area. In terms of the web, our internal funding is actually fairly small. So, and all of this is run on a small internally funded thing. So we're trying to get a basic thing, and when we get specific applications, we're going to have to tune and do those sorts of things. So in some cases, there's as I said, there's a hierarchy of this. So in some cases, it may actually be useful to do a hierarchical graph and do those sorts of things. There's actually a lot of challenges. So we can draw on our web, using our web service, graphs of up to 10,000 nodes in under 30 seconds. Which is actually, that took us a while to get there, because just laying out large-scale graphs on demand is a technically challenging thing to do. I don't know if I answered your question. So we have a couple of other, so if there's a specific law that's of interest, so we did some, so for instance, so in 2012, Congress passed the Veterans Access and Choice Accountability Act. This was the law that was passed after all of the stuff that was going on in Arizona with wait times and all these sorts of stuff. It's a big restructuring of the VA. So we've got that particular law here and all of the references to it and a couple of different views of this, so we can go down and look at it from, we can break it out into pieces and draw a graph of it in pieces rather than the whole of it. I think that's one of our challenges, is how do we present this information in a way that it's useful for non-technical people. Right now it's sort of an exploratory capability where you can interact with it and see what's being written about it and explore it and try to see, so if we were just doing a search in Google or these other sorts of stuff, you're not going to get out that these two different parts of the law are both referring to the same thing. And those are the sorts of things we're trying to help them think about and move towards understanding those sorts of things about it. Ultimately, what I want to be able to do is to say something about the structure of this and measuring of this sort of a graph. So, so the average degree in this is 1.5, and there's 81 edges and 80 nodes in it. Well, okay, that's sort of something, but I can compute path lengths and all other sorts of stuff. But is any of that useful in this context? I don't know yet. It may be, but it's going to depend on what you're trying to do, and it's really going to depend on what you're trying to do. So we sort of have four things we're trying to do in this sort of thing. One is just we want to be able to automatically ingest these sorts of policy documents and turn them into graphs and networks, extract topics, and all of these sorts of stuff. So we want to have semi-automated methods to extract, clean, and deal with these sorts of graphs. The U.S. code is actually pretty well written. Code of Federal Regulations is pretty well written. Okay, in my view, is pretty well written. When we went and looked at the VA stuff that they publish on their website, it's a bunch of Word documents with spelling errors, punctuation errors, and all sorts of stuff. So that's sort of a challenge in and of itself. The second thing is then using human language technology to extract context around all of these sorts of stuff. So can we extract the reasons why things are referring to each other, entities, topics, and all of these sorts of stuff. We could build a topic graph about the parts of the law that are talking about a topic and look at that and ask questions about that. Sort of the big unknown part is how do we measure these graphs in meaningful ways. So one of the hypotheses is that if we have data at the bottom about outcomes, we can use that to measure, to analyze how well particular structures in the graph are working. There's some other sorts of stuff. So when we get to, when we have reasons why things are citing, we can hopefully be able to pull out circular logic, things that are referencing, things that are referencing in circles, references to things that don't exist, any of those sorts of stuff. And then the last sort of thing is what I was showing is we need an interface in which people can interact with this and play with it, both from just as a way in which to better understand their system and the laws that they're dealing with, but ultimately, hopefully, to measure and analyze these sorts of things. This is sort of so I talked about the network creation. We're dealing with 3 different types of documents. So the USC is actually nicely written in XML where references have ref tags around them. Okay, I'm almost done. Yeah, I got time. I'm fine. So this has reference tags around it that are nice. Turns out the Code of Federal Regulations is written in XML, but nothing is reference tagged. So how do we pull out that? And then as we go into internal policy stuff and military strategies, we have unstructured documents, we have scanned PDFs, PowerPoints, and all of these sorts of things that agencies treat as authoritative documents. It can be a PowerPoint presentation, and that is their document of record for what they're doing. And we need to be able to pull out information from that and feed it into these sorts of networks. So we build a network, and then we run human language technology type stuff to improve it and make it better. I gave you the demo already. And I guess the last stuff is, I've talked a little bit about this. One of my goals is trying to figure out how to make complex networks more useful for the government and sort of in these applied sort of range. And a lot of this comes down to that topological characteristics are topological measures of networks. They have nothing to do with how it functions. So how it functions, you need to understand the dynamics of it. So one idea that we've been throwing around is, can we effectively linearize a dynamic network down into a static graph and then use the typical topological metrics to analyze that? So that would be 2 things are connected because they're functionally related, not because they're topologically related. I talked about the second one. Searching these combinatorially large graph spaces is a hard problem. The typical ways, so typical gradient following methods and those sorts of things don't work, especially in power grids, because nearest neighbor things, you can't you can't traverse the network in order to find where these things are very well. What else is on there? Yeah, so change over time. So most of the stuff that I see on all of these sorts of networks things are static graphs. So one thing I'm hoping we'll be able to do is look at things like the United States Code over time, and we can ask questions, has there been or is there a phase transition that's going to occur for the size of the giant component in that? And yeah. Okay, I don't need to go through all of these. Since I get asked this a lot, what do we use to do all of this sort of stuff? The answer really is, what's your favorite thing that you like to use? Mathematica and MATLAB, we're using Neo4j as a graph database. I showed you a little bit with NetLogo to do prototypical agent-based modeling. There's some there's Mason and some other Java-based agent-based modeling systems. There's a big push right now to do web-based things in JavaScript. and there's people who like R, but I'm not one. Yes?
Obamacare got in real trouble because of this buried language in some places. Would all of your network analysis allow somebody, when they were trying to make a change in something in one of these levels of federal code, to understand what was connected to that so that they could make a change that then didn't result in things that were kind of contradictory to each other, which forced us to support lawyers?
I think, so the answer to your question is not today, but my hope is that, so that is where we're trying to get to, is those sorts of questions. So one thing that comes up, so given a Congress is thinking about a law or has just passed a law, what is the, they struggle a lot with how is that going to affect us? And the time it takes them to figure that out is months or years. So MITRE actually is running a assessment of the Veterans Choice and Affordability Act joint with RAND, the VACA law that I talked about before, joint with RAND, that's ongoing now, and the law was passed over a year ago, where they're trying to figure out what it is and what VA needs to do because of that. So the time it takes agencies to implement changes is years. Part of that is it takes forever to the government to do things. Part of that is these agencies are actually incredibly complex things, and they're not, and you've got stovepiped organizations, stovepipes within it, and stovepipes within stovepipes, and of course agencies are stovepipes. So you've got groups that don't talk to each other. When people say, it was just a website, it is just a website, but it's a website that needs to hit 6 different agencies in order to verify your information and get you started in the process. So you have to hit Social Security, IRS, and I forget the other ones. So it's a complicated ecosystem.
Would it be fair to say the way we currently do this is they pass a law and then they wait about 5 or 10 years to see what happened?
Yeah. What we do right now is the lobbyists write a law and then they pass a law and then we wait to see what happens. Yes?
So let me ask you a different question. You're coming back after having been a student here. The question is really, how are you evaluated in terms of what you do at MITRE? I can look at assistant professors and I understand the tenure process and what sort of the expectations are. How does that look from your perspective?
That's a good question. So the short answer is an incredibly convoluted process. So we get evaluated. So we've now moved to a new process that was supposed to be simpler, that takes more time. So we are on our roles, responsibilities, and results. So when I first came in, I came in so my role was to be part of technical teams doing good technical work. That's basically the main way in which being part of a tech center we're evaluated. Are we doing good technical work with sound mathematical basis behind it? The other big part of it is, can you communicate in an effective way to non-technical people? So I had to brief non-technical people and technical people that don't have the time to dig in too deep in that. So I had to brief the chief technology officer of the IRS to talk to them about the performance of the ACA system, computer system. So the IRS's Affordable Care Act systems all worked perfectly fine. There were no issues there. Part of the main reason was they got almost no transactions from HHS, but that's another issue. So we did some work trying to help them estimate what their arrival rates were going to be, try to get them to think about that in terms of a distribution rather than just a number. So here's what we think it's going to be, but if we run a simulation, we can give you a range of estimates, and then it's sort of a risk. Then you've basically got a risk-based decision. How much resources do you want to do towards that? So it's really doing good technical work and what roles are you in. So
and that's evaluated inside the company.
That's evaluated inside the company, and promotions and pay increases are all done based on primarily those 2 characteristics, and who you know, of course, because it's a company.
May I assume you're finished?
Yes.
Okay. Let's thank you.